Hello class, welcome to the next segment in the vector lecture, and in this segment we're going to take a look at two different ways to mathematically represent a vector quantity. And the first one we're going to take a look at is maybe the simplest, maybe not, but there's two different ways that you can represent a vector quantity. One is by a Cartesian notation and the other is by what's referred to as a polar notation. In a Cartesian notation, you represent a vector in terms of its basic x, y, and sometimes z components if you were working with a three-dimensional vector. But if it's a two-dimensional vector, then you're only concerned about the x and y components. And that's in contrast to a polar representation where you outright state the magnitude and an angle that represents the direction of the vector quantity. But as we'll see, the Cartesian representation also contains information on the magnitude of the vector and what direction it is headed in or pointed towards. So let's start off by taking a look at the Cartesian representation of a vector. And this is represented mathematically in terms of I hat, j hat, and k hat, which for our intents and purposes, you can just think of this as whatever number is in front of the I hat, that's how many units in the positive x direction your vector quantity extends. And whatever value is in front of the j hat unit vector is how many units it extends in the positive y direction. And the value in front of the k hat is how many units the vector extends in the positive z direction. So if you have positive numbers in front of the I hat, for example, then you've got a vector that points in the positive x direction. If you have a negative value out in front here, then you've got a vector that points in the negative x direction. And the same logic also holds for the j hat and k hat. So if you have a positive value out in front of this j hat unit vector, then you've got a vector that points in the positive y direction along the positive y-axis, and you have a negative value in place here, in place of this variable y in front of the j hat component, then you've got a vector that points in the negative y direction. And the same thing for the k hat. If you have a positive number in front of the k hat unit vector, which is the reason why they're called unit vectors is because they each have a magnitude of 1. But the unit, if you have a number in front of the k hat unit vector, then you have a vector that's extending in the positive z direction, and a negative value means it's extending in the negative z direction, which usually in meteorology, in the realm of meteorology, the positive z direction is upward and the negative z direction is downward. So, and also just sort of a nomenclature thing, usually a vector quantity is notated by, usually it's, if it's on a computer or part of a publication, usually it's bolded, but sometimes you can also have you can just notate a vector by just putting a little arrow over it, or doing both, just bolding it and putting an arrow over it. But let's take a look at an example just to sort of better illustrate what exactly I mean by the numbers in front of the unit vector. So let's consider this vector quantity that's given on the screen here, where some vector v is equal to 5 I hat plus 6 j hat plus 0 k hat. So going back to what I said earlier, the number in front of the I hat unit vector represents how many units in the x direction the vector extends. So in this case, I have the number 5 in front of the I hat here, which means that the vector extends 5 units in the positive x direction. And the reason why I know it's positive x direction is because this number itself is positive. If it were negative, then it would be going in the negative x direction. So here this extends 5 units in the positive x direction, which might be represented as such. But that's not the full story. We still have to account for how much it extends in the y direction. So since I have the number 6 in front of the j hat unit vector, that means I've got a vector that is extending 6 units in the positive y direction, which, going with the standard Cartesian grid, would give us 5 units over to the right of the screen and then 6 units up the screen. And if we want to actually see what that vector looks like, what you have to do is you have to attach an arrow where the tail of the arrow goes toward the beginning here and the tip of the arrow goes toward the end. And this is where the idea of graphical addition comes into play, where if you add vectors, you take the tail of one vector and attach it to the tip of the other vector. So that's kind of what's going on here. We're adding a bunch of vectors here where we're taking the tail of each vector and attaching it to the tip of the vector that comes before it in the addition. So if we do that exercise, then we can get something like this. And if we want to see what the end result of all that addition is, we connect a line starting with the tail of the very first vector in the addition and connect it to the tip of the very last vector in the addition. So that would give us a vector that looks like this. So this entire vector, 5 I hat, or 5 units in the x direction, plus 6 j hat, or 6 units in the y direction, would give us a vector that looks something like this. 5 units over, 6 units up. And if we take a look at another example that involves the same nomenclature, here we have a vector quantity that's represented as negative 4 I hat plus 2 j hat. Again, we're not going to worry about the vertical component just yet. But here, since I have a negative value out in front of the I hat component, this tells me that my vector points in the negative x direction. So negative 4 I hat means I have a vector that extends 4 units in the negative x direction. And I still have a positive number out in front of the j hat, so that means I've got a vector that extends 2 units, whatever those might be. Here we're going with just unitless numbers, but these could be units like meters per second if it's velocity or newtons if it's force. But this would be a vector that extends 2 units in the positive y direction. So that would give us something like this. And then doing the same thing that we did before, again, you can sort of think of these as adding a whole bunch of little vectors together, or just 2 large vectors. What we have to do now is we have to attach, to get the end result of that, we have to draw a line starting from the tail of the very first vector, and then connect that with the tip of the very last vector to get something that looks like this. So this entire vector quantity can be represented as something like we see on the screen here.